Nobody's talking. What's the bug? Who sees the bug? Raise your hands. Why aren't you talking? You should be at least saying, do you see the bug? Discuss this, really, seriously. So I've got 1, 2, 3. Who else sees the bug? This bug is super easy to see. Super easy. So somebody shout out, what is the bug? Memory leak. Why did I say it's super easy to see? Super easy. I can determine this. Do you know the program graph? I guess that's a memory thing. Okay, so that's a command line procedure that does regular expression search. It just searches for tasks. I can find this error with graph. What's missing? Free. This program never calls free. So long as it calls, so long as push is called once, now it's possible push is never called, but so long as push is called once, I've allocated something, I never free it. That's a memory leak, right? But it seems to work. I ran it, it works. How do I know, so that case is simple, but most memory leaks are not so simple. How do you know? If you're in 221, I think you've seen this. I have to run this on a given machine. So I'm on a Linux machine because I'm going to run this program called Valgrind. And Valgrind doesn't exist on Mac, or at least I can't do they on Mac. So what I did is I just copied all the files from my Mac here to Linux. And you'll notice that one of the files is the executable file. This one has the star by it, ls can do star next to things that are executable. And its name is stack start. Why can't I do this? Look at the error message. Exec, which means short for executable. Format error. Cannot execute binary file. Why not? Well, I've never said this before, but every operating system has its own, or could have its own format for executable files. The executable file is an image of what will be executed, but it also is formatted in a specific way to an operating system. So when you build for the Mac and you build for Windows, that executable can only run on the Mac or on Windows. So if you copy the executable here, it won't work. So what you need to do, and I'm doing this with a makefile, you did make files for this assignment. I say make clean, which deletes all of the object files and executables, the things that will be recreated when I just say make. Now I've built that for Linux. I know I can run it. And it works, okay? But now what I'm going to do is I'm going to run this using a program called Valgrind. So what Valgrind does is, given an executable, it edits the program at the machine language level to insert instructions so that when the program runs, it keeps track of certain things that Valgrind at the end can report. And one of the things, and this is the thing we're looking at, is it keeps track of memory allocation so that it can tell you at the end if you have a memory leak. So if I run this, it will say, it'll print out a lot of things which for this class we're going to totally ignore until you get to the end. And there's two sections here. One is heap summary, and it says, in use and exit, 32 bytes in 2 blocks. Don't worry about the blocks. That's that. There's not supposed to be anything in use and exit. Okay? And then it also says, leak summary, definitely lost 32 bytes. Right? So Now, this memory leak, if you weren't in a class like this, wouldn't matter. I mean, you just run a short program that has some leak, and the program terminates. Who cares? But we care because we're trying to, help you learn not to make these errors. And the only reason you really ever care about memory leak is a program in real life. Because a program is meant to run for a while, like a web server, game, an operating system. And then you wouldn't really care about this because that 32 builds up, over time. Okay. So from now on, with a few exceptions, when we get to threads, it will tell you about every time you run a program now, you need to run valgrind on it, and you have to submit programs that are memory leak free. And the only way you really know is by running valgrind. I should say this one thing, though, is that valgrind does dynamic error checking. What it does is it takes a particular execution of the program and determines whether that execution has a memory leak. So if it says no leak, that doesn't mean it doesn't have a leak. It just means that that particular execution of those parameters didn't have a leak. It's not doing static analysis. Static analysis for memory leaks is extremely hard to do. And in general, it's intractable. Okay? But dynamic is kind of easy. You just run it, and you just keep tracking it, in a sort of side data structure. How many, what was it valid and was it free? So the end was free. And it actually can detect some dangling pointers too, but not all of them. But we're not going to use it for that. Okay? So that means, just like any kind of testing, when you run something through valgrind, you have to run it with different kinds of parameters. For example, if you were to run this program and never called push, it wouldn't have a memory leak, and valgrind would be fine. So anyway, as a memory leak, step 2 here is fix it. Change this code so that it doesn't have a memory leak. And also, hopefully, so it doesn't have a memory leak. So which procedure do I have to change? Pop, right. So what do I have to add to pop? Well, okay, yeah, we'll get to the RC part, but let's just do it the wrong way first. Free. And where will I put free? I could put it, oh, let's put it. Right there. So what I do is I make E point to this. Then I change head to point to the next thing, but in this case that's just 0. And then I freeze. Okay. So this now free, and when I return, E is a local variable, so E goes away. Now, some of you don't even know. Notice that this is not going to work. But let's just be sure that that's true. I got the answer 2. That's the wrong answer. And what happened? Now, mostly we're just going to look at this. What happened? Well, store this to what it was. So we're looking now at main. So a main has a variable called first. Well, actually, actually, initially, this doesn't exist, right? So then you call push, it creates this, push 1, puts the 1 in there, and returns that pointer, and then this ends up being the value of first. So first points there. And then it calls pop, and pop sets this to null, and frees this. And then it calls push 2. Well, in this case, as we've seen before, it's going to reuse that same piece of memory. And have the point here. And then it calls pop again freeing this, and setting this to null. First is a dangling pointer after the first call pop. It's now pointing to this piece of memory that has a 2 in the position where the 1 was before. And actually now it's been freed, so potentially it can even be changed again if the program is more complex. Right, so the problem was we're not supposed to free it if first points to it. But if you look at main, sometimes you call push, and you save it, and sometimes you don't. So here's now the problem, is that pop doesn't know if it should free it or not. If main doesn't save it, it should call free, but if main does save it, it should. So the solution is reference count. Because these are 2 different modules, I don't want them to have to know about each other. So I'll just start by, so first thing, I have to include the header file that we provide you that describes the calling signature of the 3 procedures that implement the public interface of reference count. RC malloc, RC keep ref, RC free ref. So now I can call those things here. And so I'll turn this into RC malloc, and I'll turn this into an RC free. Now, as I said before, nothing has changed, right? Because I haven't done an extra keep ref. But if I change main to put keep ref and free ref in the right spot, now I should be able to solve the problem. So that if this does point here, it won't get freed by pop. So now just give you 20 seconds. Where would you put these 2 things? Or well, how would you change? So I need to put a keep ref somewhere. Where would I put it? Where? After. Does that make sense? What if I put it here? So it's the same thing. I'm saying free, RC keep ref free. But again, this comes back to what we were talking about earlier. It's not the name of the pointer that matters, it's its value. So at this point, first has arbitrary value. It's actually, it's uninitialized and it's not a global, so that probably will cause a segmentation. But here now, so I'm in this state, I'm setting first to point to this, and I'm going to change the reference count to 2 by saying keep ref. And now when I say pop, it will free ref sets the reference count to 1. That doesn't point there anymore. So the next time I say push, this is still allocated, so it's going to allocate a new object. Its reference count is 1, its val is 2. It'll point here. But now I don't save that, right? So I don't do a keep ref, so its reference count is 1, so now I call pop again. That sets this to 0, and that gets freed. So when I get to the point of printing first val, it's still there, so that's good. And all that's left to do is I better call this at the end. So the data eventually gets freed. And now, that's not enough. I'll show you the implementation next time, but let me just make this. Oh, I didn't spell it. RC free ref. One is the right answer, right? The right answer, valve grind. And valve grind also is happy. Deep summary, 0 bytes in use and exit, no leaks are possible. Okay, that's what you want. Okay, so have a great weekend. See you later.